What would be the first question?
Okay, we're on page 6. I want us to do one more of the word problems from 6.2. I think we got there number 3, or we started number 3, right? Sorry, we could start number 3, but we didn't get through it. Okay. I think I briefly talked about it. I don't think I got through it. So let me start from the beginning here. Okay, so the rate of decay of radium. So we know that anytime we see the word rate, we know it's going to be a derivative or rate of change R prime is proportional to. So we know it's going to be in that form of y equals kx, proportional to the amount of radium present at any time. So R prime equals kr. And we talked about last Friday that if we see something in the form of y prime equals ky, it'll end up giving you y is equal to ce to the kt if we were to solve the differential equation, separate the variables, right? So we went through all that process on the previous page, number 1, right? Y prime equals ky will turn into y equals ce to the kt. So if we see something in that similar form, what do you think we can create out of this? R prime equals kr would result in what? R equals ce to the kt. So this is the general equation, but we have to. There's a lot of information provided so that we can find the c value, find the k value, produce a specific version of this equation, so that we can use it to solve or make a prediction based off of the information given. So I like to create order pairs. So time is my independent variable. The amount of radium is my dependent variable. Okay, so we want to find the earliest time that's presented in the problem. So it says, if the amount of radium at present now, if 60 milligrams of radium are present now, so that means we'll let present day be t equals 0. We always want to involve 0 to help with the numbers here. So year 0, 60 milligrams are present. Okay. Its half-life is 1,690 years. So that means 1,690 years from now, how much radium is going to remain? 30, right? Half-life. So we know that that amount will be cut in half. Half of 60 is 30. So now it's asking how much radium will be present 100 years from now. So 100 years from now, what is the amount of radium? So all this information is provided because we have all these missing variables or missing information that we need to fill in. So the 060 is going to be useful to help us solve for C. The 1,690 and 30 is going to help useful to help us solve for solve for K. And then once we have our missing information filled in, then we can use the final piece to help us make a prediction as to how much radium is present 100 years from now. Okay, so we use our equation here. Insert 0 in for T, 60 in for R. Solve for C. e to the 0 is just 1, t equals 60. So the connection, hopefully, that you're seeing is that if you have something that's involving 0, your C value is sitting there for you, right? So if you went through that process, you're going to see that your C value is going to be basically the amount of radium at the initial time. Okay, so now that we have our C value, we're going to go back to our original equation. We're going to update it so we can kind of build upon it and make our progression. Okay, what's next? Yeah, plug in the second set of order pair, right? 1690 in for T, 30 in for R. We should be able to work our way and solve for K. I want to solve for K, but K is stuck inside this expression. We want to move things away from that right side so we can get it down to solving for K. What's the easiest thing to move first? 60, right? So divide by 60. Thirty over 60 is 1/2, or 0.5. Right, I want to solve for K, but K is stuck in the exponent. What can I do to both sides to help me get that K down? Not a lot, okay? Bring that exponent down in front. Natural log of E goes away. And now the last thing to do to solve for K is what? Divide, yeah, divide by 1690. Okay, so now let's update our equation. And rewrite our radium equation with the C and the K filled in. And the reason that I want to hold on to that value instead of putting a decimal is because I want to try to improve my accuracy. So if I create a decimal version at this point, it'll decrease my accuracy at the end. So I'm holding on, even though it looks messy, I'm holding on to this exact value until the very end when I can make my approximation. Okay, so now I'm going to figure out how much radium will be present 100 years from now. So I'll insert 100 in for T. And that can all just go into your calculator. Okay, the last one here. It's a little bit different because the information that's provided for you seems a little bit backwards here. But let's see if we can go through the same. We'll still go through the same process. We'll still create our ordered pairs, but the information that's given to us is going to be slightly out of order. Okay, so in a certain culture where the rate of growth of bacteria, let that be B prime, is proportional to the amount present. So same form, right? Y prime equals KY, B prime equals KB. Okay, so I'm going to create my order pairs here. Time T in hours. And then the amount of bacteria in millions. So here we know that there is some starting time, but we don't know exactly how much there is to begin with. So I'm going to let zero, at time zero, there's some amount, and we know that C is our initial value. So we'll say that at time zero, there's some amount of bacteria that we don't know. We're going to work towards solving for C. But we know that in 3 hours, what's going to happen to that C? Triple. So what can we do to represent that? 3C. Okay, so I'm just creating something that is relationally consistent. And we know that after 12 hours, there's going to be 10 million bacteria. So I'm going to let 10 represent 10 million so that I don't have to write so many zeros. So at the end, we're going to have to multiply it by a million because we're representing everything with easier numbers. So let's see if what we can do using these order pairs. Okay. So if I plug in 0C in for this equation, am I going to make any progress? Yeah, because I'm going to get C is equal to CE to the K times 0. And it's not going to give me anything additional. So I'm going to ignore this order pair for now because I'm not able to make any progress. And also, this is what I'm going to solve for at the end. But maybe this can help me out. Okay, so I'm going to use this order pair, insert 3 in for T, 3C in for B, and see if maybe that can help me solve for one of the variables that I'm looking for. I want to solve for K. What's an easy thing to move? C. So if I divide by C, what's going to happen? It'll cancel out. Okay, so I'm just left with 3 is equal to E to the 3K. All right. What can I do to both sides? Natural log. Bring that 3K down. Natural log of E goes away. Divide both sides by 3 to solve for K. All right, so now I'm updating my equation. I still don't have my C value, but at least I can update my equation and replace my K with a specific value. So maybe the third order pair now can help me, right? Because 12 is going to help. It's going to replace what? T. The 10 will replace the B. Will that give me enough for me to solve for C? It should, right? Because looks like every variable is accounted for, and I can kind of work backwards and solve for C. So this one, we're going to enter this in the calculator. We can't enter C in the calculator, but we can enter E to the natural log of 3 over 3 times 12, get that number, divide that number to the other side, and we can just solve for C. ends up just giving me 81. Divide both sides by 81. But we know that this is in terms of what? Billions, right? So I need to multiply this by. Yeah, so move the decimal over 6 places. Okay, so usually, if the problem gives you the C value, then it feels more natural because you can just solve for C, solve for K, and then find the missing information. But sometimes you're working backwards where they give you where you're looking for the starting amount, and then so you have to kind of create a relationship with that. So you're second with a second using the second order pair to solve for K first, and then solving for C. So this feels a little bit backwards, but you're still using the same process. You're just solving for a different piece of information. Okay. The new topic that I want to go over today is slope fields. You guys can turn to page 7. Okay, so slope fields is a graphical approach to look at all the solutions of a differential equation. Slope fields consist of short line segments representing slope, steepness sketched at a lot of different points. So let me talk a little bit about kind of like the big picture here. The big picture is that when you solve a differential equation, you're having to separate the variables. You have to decide which rule is available for you to solve. But one thing that we haven't seen are problems that are not solvable. Okay? The ones that I give you on a test are all going to be solvable. Okay, you can separate the variables nicely. You're going to be able to match with a rule that's available to you, and you're going to be able to solve it. You're never going to be given a problem on a test or on the AP exam where you try to separate the variables and it just doesn't work. Okay, but there's going to be a lot of different equations that are not solvable. Okay, at least not by hand, not by us. And so the idea is that slope fields allows us to look at a visual representation of the solution without us being able to solve it algebraically. Okay, so that's really the big picture here. But really, the only thing that we have to do with slope fields is be able to create them at a small level, and also to be able to interpret them just in a very just very for very simple differential equations. Okay, so we're not going to have to deal with this in a very grand scheme, but it's going to just be just the few things that we have to be able to do for the AP exam. Okay, so these line segments are tangents to a family of solutions for differential equations at various points. The tangents show the direction in which the solution curves will follow. Slope fields are useful in sketching solution curves without having to solve a differential equation algebraically. Or it's useful to sketch the solution curves where we don't have a solution algebraically to a differential equation. Okay, so the ones that we create are only going to be at a few order pairs. You're really not going to be able to see the visual picture that you're going to need. So there's two types of problems. There's ones that are easier where you just have to create the slope field enough for you to demonstrate that you know how to create a slope field. And then there's also ones that you're not really creating because it's just too crazy. Like you look at page 2, this is like hundreds of points. You're never going to be asked to create something as large as this, but you're going to be asked to be able to interpret it, to be able to look at it and be able to identify certain things that they're looking for. Right. So yeah, I just want you guys to make sure that you understand that you're never going to have to create something as tedious as 100 of points. Okay, the most is maybe 6 to 12 points. Okay, so this is how we create slope fields. We identify order pairs indicated on the graph. We plug in the order pairs into the differential equation, find slope. Sketch a short line segment representing the slope through the given point, and then repeat this for all remaining order pairs. Okay. All right, so first thing we do is identify the order pairs. So on the AP exam as well, if you're asked to sketch a slope field, they will identify those order pairs with very distinct indications, right? So these are the order pairs that we're going to be filling in the slope field for, okay? So it's only going to be at those 8 points. It really doesn't matter which order you create the order pairs, but just so that we can just stay together here, I'm going to list out all the order pairs. So we have an order pair at this is my origin here. At -1, 2, -1, 1, -1, 0, -1, -1, and then 1, 2, 1, 1, 1, 0, 1, negative. Okay? 8 order pairs. So what we're going to do is you're going to take the order pair each and plug it into dy dx. Now I want you guys to remember that dy dx is basically f prime. Okay? This is basically your slope formula. Okay, so I don't want us to lose connection with dy dx. I don't want us to think of dy dx as something that we haven't seen before. We know what this means. It just means that anything you give it, you're going to get a number, right? A number is going to represent how steep that point is on that curve. But dy dx is just a slope formula. It's just f prime from first semester. Okay. So -1, 2, we insert it in for x and x minus 2y. So we get -1 minus 4, which is -5. So through this order pair, you're just going to try your best to represent -5. Okay. It's a pretty steep slope. So that's good enough. On the AP exam, they're not going to measure how accurate you are with your, right? If you are able to represent a negative slope, that's good enough. Okay. -1, 1, we insert that into our order pair. So -1 minus 2 is -3. So -3 is not as steep as -5, but it's still a negative slope. And we go down the line. Okay. -1, 0, -1 in for x, 0 in for y. -1 minus 0 is -1. Okay. -1, -1. -1 minus -2. So -1 plus 2 is 1. So it's going to switch back to a positive slope here. Okay, so you guys can finish off the rest of the order pairs. Okay, any questions so far with part A? What if dy dx was equal to 0? What would you do there? What would you do through the point? Yep, horizontal line. What if your dy dx was 9 over 0? Undefined. How would you represent undefined slope? Say it again. So yeah, vertical, but vertical slope is undefined. It doesn't exist. So what you do is if you see undefined slope, you're going to leave that empty. Because technically a vertical slope doesn't exist. So if you see undefined slope, that's empty. So there's only 4 options that you're doing, right? Either negative slope, positive slope, slope 0, horizontal line, or undefined, which is empty. So that means you don't touch the order pair. Okay, so if you're comfortable with those 4 options, then creating these should be easy. Okay, any questions with those 4 options? All right, so let's see if we can try part B here. Let me put the order pair in a certain order so you can follow it, easier for you to check your answers. And I want us to keep reminding ourselves that we know this notation, okay? If I ever ask you for a slope, you're going to use this information, right? I don't want you to think of this as something foreign, something that you don't recognize, right? There's just a slope formula for a graph that we don't see. Right? See if you can find y prime or dy dx and make your appropriate segments, notations through those order pairs. Okay, check your answers. Any questions? Okay, so I think creating slope field is pretty easy. I think the harder thing is interpreting a slope field. So imagine, because right now you're looking at these slope field, these segments, it doesn't really mean anything. You don't really see a shape that's coming out at you. So the next page, we're going to see a slope field completely filled out. And we're going to be able to make interpretations about what it represents, what a solution could look like. Okay. All right, so let's go to the next page and spend some time with this slope field that we see here. So this is a slope field that is completely filled out, right? So hundreds of points all filled out with these short line segments. We see either really steep positive slopes, we see either a gradual positive slope, we see slope 0, we see positive slope and gradual slope, or gradual slope and really steep positive slopes. Okay. So, but it says determine the differential equation being graphed by each of the slope fields below. Then sketch a solution that passes through the indicated point. So we'll talk about that second sentence later. But first, we're trying to determine the differential equation being graphed. So for one of these options, this is the picture of the slope field for one of these differential equations. And we're trying to figure out which one is going to be the one that fits the best. Okay. So one thing I like to do is to be able to look at this and just make some general observations. Okay, do you see some, can you make some general observations about the quadrants, or where you see positive slopes, where you see negative slopes? What do you notice about most of the slopes that you see here? Mostly positive, right? Where do you see a place where the slope is not positive? Where x is 0, right? So we know this has to be true, that at x equals 0, I should be getting dy dx equals 0, right? Because I see the picture in front of me. So what I like to do is I like to plug in and just see if I can eliminate ones that are obviously not true, right? If I can't fulfill this condition, then I know that it can't be an option for me. So at x equals 0 for the first one, am I going to get slope 0? Yes. Okay. So I have to keep that as an option. I can't eliminate that yet. If I plug in 0 in for x, am I always going to get 0? Yes. So I got to keep that. Okay. If I plug in 0 for x here, am I always going to get 0? No, right? Because the y could be something else, and that could be a different number, and that should, I should not be getting a consistent 0 all the way through. So that's nice. I can eliminate option C because I know that that's not fulfilling this condition that I see here. At x equals 0, when x equals 0, am I always getting 0? Well, unless y is what? 0, then this should be undefined, but I don't see anything undefined here, right? Everything is filled in. So this is not going to work. Okay. And then natural log of 0, do you know what natural log of 0 is? Not 0, it's actually this is a natural log graph. Doesn't exist. Yeah, there's a vertical asymptote there. So we know this can't be it, right? We don't see it does not exist here. So we're down to two options. Right? Either x cubed or 3x squared. Now, what other observation did you guys say before this one? Slopes are mostly what? Mostly positive. Do you see any place where there's a negative slope? Yes.
So you said option
Mhm.
zero.
Mhm.
You said there's 0.
So 0 over 0 will be undefined, and if I have undefined, that means I should see some empty spaces. Because all these are filled in with slope zeros, right? All filled in with zeros. Okay. So we say mostly positive because the fact that there are some that are zeros, but do you see any negatives? There's no negatives. No negative slopes whatsoever. So we're down to two options here. Which is the option that will always produce a positive value? B, right? Because C, or I'm sorry, part A, if I plug in a -1 or -2, any negative x value will give me a negative value, but I don't see any negative slopes here. So that doesn't fit this condition, right? So I like to look at slope 0, slope undefined, positive and negative slopes, and see if I can make some general observations and eliminate the wrong choices. But it's going to have to be this one, right? This is the only one where the slope is 0 at x equals 0, and I'm getting for sure positive values everywhere except at 0. So all slopes positive except the y-axis. Now, there's something else that I want us to be able to do here is, let me erase this, I don't need this. So that's one way to look at a differential equation or slope field. The other way is this, okay? I want you to look at this pattern here. So imagine you're taking a big, you're looking at this as one big graph. Do you see a pattern here? What shape do you see? So if I follow through that point, if I kind of just follow along that, what does that look like to you?
Oh, isn't that? Okay, that's not-
Okay, is it a linear? Is it a quadratic? Is it a cubic?
Cubic.
Cubic, okay. What's the degree of a cubic function? 3, right? So this resembles an x cubed graph. Okay, we don't know exactly, the stretch or, because we have all these different variations, right? Depending on the c value, it can be shifted up, shifted down, but through this point, it's going to be this graph. So it's going to be in the x cubed family. Good. Yeah. So I want us to make that connection here. This is the derivative, right? But the x cubed. So let's do this. Let's solve this differential equation and see that connection. Okay. So if we solve this differential equation, we should get something that is going to resemble the shape of the graph. All right. So this is kind of at the microscopic level. We're looking at each individual order pair. But once we solve the differential equation, it should resemble the shape of the graph in front of us. Okay, so let's separate the variables. I'm going to cross multiply here. Okay. Variables are separated. dy dx are nicely in their right spots. I'm going to take the antiderivative of both sides. There's a 1 sitting here. Okay. What's the antiderivative of 1? 1 dy. Y. What's the antiderivative of 3x squared? 3x cubed over 3 plus c. What happens to the 3? Cancels out. X cubed plus c. Okay, so this graph is going to resemble x cubed plus c. And the reason why there's a plus c here is because it depends on what that c value is, right? That c value could be 0, it could be 1, it could be 2, or it could be 3, and that's going to dictate your y-intercept. So depending on what that y value is, on that y-intercept, it could be any variation, right? It could be here, it could be down here, right? And that c value is just going to push that graph further and further up or further down, but it's still going to resemble that shape. Yeah. That's right. Yeah. If you know that it's cubic, you can find the derivative, and the derivative should match that option as well. So it can go both ways. You can look at it from the picture's perspective and get to the derivative, look at the derivative's perspective and match with your slope field. So it's nice to have those options. Sometimes though, problems are presented in a way where you can't solve it, and you're forced to have to look at those individual characteristics to narrow down and this one though is solvable. It's nice to see that connection, that the picture should match your solution. Okay, I want us to do one more here, number 3. So number 3 here, we don't know what's going on the x-axis. Okay, the reason why is because there could be a slope 0 that's being hidden by the x-axis, or it could be slope undefined. So we really can't depend on what's happening here. But we do know, what do you know about the y-axis? It's definitely undefined, right? Because there can't be any vertical lines here, and if there was a slope field, it should show, right? It should show for us, right? So here we can definitely tell that at x equals 0, my dy dx should be undefined. Right. So I want to kind of list out some just general observations. Are there any observations that you can make about maybe the quadrants? Yeah, so quadrant 1 and quadrant 3, I'm getting slope what? Positive slopes, right? What about quadrant 2 and quadrant 4? So basically, if I choose any order pairs in these regions, I should get these characteristics. So this is nice here. That means if I plug in 0, I should automatically get undefined. So A, am I getting undefined here? No, here, eliminate that. Undefined here, no. C, D, yes. And then E is still good. So we know already our answer is going to be 1 over x. Okay. But let's say this was not enough and we had to kind of go a little further, right? Any quadrant in quadrant 1 and quadrant 3 that I plug in, 1, 1, 3, 3, 5, 5, I'm getting positive value. Any third quadrant values I plug in, -1, -3, -4, -5, I'm getting a positive value. Any quadrant 2 and quadrant 4, I'm getting 1 positive. The x and y values are always different signs here, so that's why I'm getting a negative. Okay. And if I were to solve this, it would resemble these linear graphs that we see in front of us. Okay, so we'll finish this tomorrow. No homework tonight, and we will finish this, and we'll go back and review more, practice more differential equations Tuesday, Wednesday. Okay, no assessments this week.
But I see 2 different.
You mean 2 different? What do you mean problem?
Like on the above the x-axis, it's like that's line on.
So these are all lines, right? So really, it just depends on what the C value is. These are all just all linear graphs. So if we were to solve this differential equation, it should produce a linear graph.
Like,
There's no curve, right? I don't see any curves here. So.
okay. But is it so
Like the first one, there were curves, so you knew that it was going to create like something that's like an x cubed.
oh.